Okay, welcome back to section 4.2. So this is again another lecture from Monday. A repeat of another lecture from Monday, but okay, I'll stop complaining about what happened before now. All right, now we want to focus on in section 4.2, just the constant coefficient nth order, homogeneous linear ODEs. Yes, that's a mouthful. It takes 5 minutes to say the equations you want to work on. So that's equations that can be written like equation 4, where the A's are just constants, and we pick the numbering scheme, so it's kind of easy to keep track of which A goes with which Y, which derivative, I should say. So remember, in the last lecture, we said, okay, suppose you guess that the solution is an exponential. Again, we don't tell you about the guesses that don't work. We only show you the ones that do. So guessing an exponential works nicely because, as we showed before, every time you take a derivative, you get a power. And we did that little calculation to show that you quickly get to see that the characteristic equation has to hold. Okay, so, okay. Now, we want to look at different cases of solutions you get when you solve the characteristic equation. And in the process of doing that, we're going to run into some troubles because it's generally hard to solve higher order algebraic equations. So things of this form. All right, so let's start with a simple example. Okay, so we're going to start with this problem. So y fourth derivative plus the third derivative minus 7 times the second derivative minus the first derivative plus 6 times the function equals 0. And we're in principle going to work on this. This is the 0th order, the first derivative, the second order derivative, even though it's a little blurry, and the third derivative. I give you specify those at t equals 0. Okay. So how do we start to solve that? You write down the characteristic equation that goes with that. And how do you do that? Just like we did with the second order equation. You take every derivative converts to the same power lambda. In other words, the fourth derivative becomes a fourth power lambda. Third derivative, third power. You keep the sign in between. Minus 7 times the second power minus the first power. And this is the 0th derivative. So you get the 0th power lambda. Okay. And now you run into the first problem. How do you solve a fourth order equation like this? You can't, you can try to factor, but man, trying to factor without using a method will take forever. It's really hard. So there is a trick. There is a good method to use. And you should have seen this in high school. But usually, like I did in high school, and if not there, you certainly should have seen it in college algebra. So this is called synthetic division. If not, now's the time to learn it, or you'll never survive the homework problems and the next test. Okay, so how do you do synthetic division? It's basically a trick. It's not a trick. There's a theory behind it, but we're not going to go through the theory. It would take too long. So what you have to remember is you need the coefficients of the highest order term and the coefficient of the constant term. Okay. And so what you do is you write down all the possible factors of the coefficient of the highest order term. So here that's lambda to the 4th. And the only factor of that is plus or minus 1 because it's 1. It's always plus or minus in front of everything. And then you look at the possible factors of the constant term. So that's 6. What divides 6? 1, 2, 3, and 6. So the possible factors are plus or minus all of those. And now you get the possible roots of the equation by dividing all the possible factors of the constant by all the possible factors of the highest order term. Now, since this is 1, it's much easier. So you only get all the possible factors of the constant as your possible roots. All right, now how do you actually get which one is a root? So here comes the method. Again, it's another method that you just need to learn, and it's pretty easy. It's just a little routine. I'm gonna rework this because I think that would be hard to follow watching me do it. So without seeing me do it. So let me rework this one for you. Okay. So our possible roots, I'll put it so you can see those. So our possible roots, remember this, because I'll have to cover this part up to be able to see everything. Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Okay. All right. So what we get, and this is the equation that we want to solve. So here's how synthetic division goes. You copy down just the coefficients from your equation. And you need all the coefficients. So if it's like a fourth order equation, there's no second order term, you still have to include the coefficient 0 for that second order term. So fourth order coefficient, third order coefficient, second order coefficient, first order coefficient, and the 0th order coefficient. Okay, just copy them down. It's a good little place to do this is here. Now you're going to put right there the number you hope is a root. So right now, I hope that plus 1 is a root. We'll be able to tell if that's a right guess or a wrong guess by the method. All right, and now the method for synthetic division says copy down the first guy. So whatever's there, copy it down. And now you multiply your guess at a root times these guys. So 1 times 1 is 1. Put that here and add. Multiply, then add, not subtract. Okay. So 1 times 1 is 1, and when I add it, I get 2. And you keep going. 1 times 2 is 2. Put that there, and add, you get minus 5. Okay. Minus 5 times 1 is minus 5, and add, you get minus 6. 1 times minus 6 is minus 6, and you add, you get 0. If you don't get 0 over in this part, well, this is, when you get 0, think of it as bingo, you found a root. Anything other than 0, bam, too bad, you missed. You got to try another one, okay? Now let's remember our algebra terminology. So 1, we just found out that 1 is a root. So what is a factor of this equation? If something is a root, then lambda minus that is a factor. Okay, so what synthetic division has told us so far is that the polynomial equation we started with, which by the way, we want to be equal to 0. So if we need to be able to So we need to be able to factor this thing so that completely, so we can tell what the lambdas are that make it 0. Okay, so now we know that lambda minus 1 is one factor, but how do we know times what? These things tell you what the other terms are. So you started with a fourth order equation, you factor out a lambda minus 1, and so this one starts with the third order. So this is the coefficient of the third order. So it's 1 times lambda cubed plus 2 times lambda squared minus 5 times lambda minus 6. Okay, so synthetic division spells it out for you. Now, are we done? No, because it isn't easy to factor that one either. We have to do synthetic division on that one. Okay, so we do synthetic division again. Okay, so now we go 1, 2, minus 5, minus 6. Okay, and what are our possible roots? It's all the possible factors of 6 divided by all the possible factors of 1. Because it's the constant term divided by this. Well, so 1 doesn't change things. So that's going to be only the factors of 6. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Oops, sorry, squeezing that in there. Okay. So now we make a guess. I'm going to guess minus 1. Okay. So we copy the 1 down, and now we start multiplying and then adding. So 1 times minus 1 is minus 1. Now I add, I get 1. 1 times minus 1 is minus 1. I get minus 6. Minus 6 times minus 1 is plus 6. I get 0. So bingo, I picked a root again. So now we have that our original thing that we started with, our fourth order, which we had factored to lambda minus 1 times this cubic. Now we know that minus 1 is a root. So what's a factor of that cubic? It'll be lambda plus 1. Minus, you always do lambda minus the root. So minus and minus 1 is plus 1. And now what's the next term? It's given by these coefficients here. We started with a cubic, so what we get from here will be a quadratic. So this will be lambda squared plus lambda minus 6. And now that's a quadratic and an easily factor 1. So just factor it from here on. And on the test, I saw a lot of people want to use a quadratic formula on every single equation. And if the people who did that, it generally worked out badly for them, because they would sometimes if it's easy to factor, just factor it. Sometimes a quadratic formula is very easy to mix up, make a mistake in the arithmetic, and then go way off track. Okay, so here, how do you factor this one? 6, it factors with 2 and 3. This says the signs are different. The bigger one goes with the plus. So this will be lambda plus 3, lambda minus 2. Okay, so all the roots are, so the solutions are lambda are 1, minus 1, minus 3, and plus 2. Okay, so those lambdas came from the solutions y is equal to e to the lambda t. Okay, so every time you get a different lambda, you get a different solution of the inhomogeneous equation. So y, the homogeneous equation, sorry. So y1 of t is e to the 1 times t. y2 of t is e to the minus 1 times t. y3 of t is e to the minus 3t, and y4 of t is e to the 2t. Okay, so the general solution of the homogeneous, constant coefficient homogeneous example we started with, this, let me get back to it, this example right here. The general solution of that is a linear combination of these 4 guys. So fourth order equation, you need 4 linearly independent solutions. Exponentials, we haven't learned how to check that quickly yet, but we will by the next section. Just we'll trust that it is, but basically exponentials with different exponents are always linearly independent. So this is going to be C1 times the y1 plus C2 times y2 plus C3 times y3 plus C4 times y4. Okay. All right, so that's our general solution. But we are not done, because the original problem had these initial conditions for y at 0, y prime at 0, and so on. So you're going to need to compute the derivatives, first, second, and third, plug in the value at 0, and see what happens. Okay. So let's do that. I think that will be not so bad to follow along. Sheet of paper here. Okay. So it's important to learn that synthetic division. Watch that part of the video a couple of times if you need to. Okay. All right, so we wrote down, here's the general solution. I wrote it in a slightly different order when I did it earlier. So I had the 2t first and the 3t second. That doesn't matter. Okay, now we have to start computing the derivatives to check the initial conditions. So you just differentiate. So when you differentiate, you get C1 e to the t. And then you get minus C2 e to the minus t. And when you differentiate this guy, you get a power of 2. And this guy, you get a power of 3. Okay. When you differentiate again, you just get a 1 here. Now the minus 1 makes it a plus C2, another factor of 2, so you get a 4C3, another factor of 3 in this one. Okay. And then the third derivative, you do the same thing again. So your coefficients become 1, it's this. That's easy, right? And now we have to plug in the conditions. So the first condition said y at 0 was 1. So 1 has to be equal to this thing evaluated at t equals 0. So at t equals 0, all the exponentials vanish. So that says, not vanish, sorry. It's e to the 0, so that's 1. So at t equals 0, you get 1 is equal to C1 plus C2 plus C3 plus C4. Okay, so that's one equation. The second condition, the second initial condition that we were given said y prime of 0 is 0. So now we go to y prime at 0. That has to be 0. That's what we were given. And now we go to the equation for y prime, stick in t equals 0, and see what that works out to be. Every exponential, when it's raised to the 0 power, is 1. So that gives me a C1 minus C2 plus 2C3 plus 3C4. Second equation. Now we do the same thing with the y double prime equals minus 2 condition. You plug in t equals 0 in this one. It has to be minus 2, and what that gives you on the other side. Okay. And then you do the same thing with the y3 double prime at 0. All right, and now what that gives you is 4 equations in 4 unknowns. I don't know if you remember doing that in high school or college algebra, but that is, if you just do it by regular algebraic methods, it's really bad. And if you try to use Cramer's rule, you find a ton of big determinants. That's kind of miserable too. In a day or two, I'm going to probably maybe Wednesday's lecture, I'll show you a quick way to do it. If you've done linear algebra, you'll know this already. If basically you're row reducing the equations. If you haven't, it'll be new, but it makes this kind of solution really go fast. Okay, if you worked it out long algebraically, those are the solutions, but I'm not going to do that right now. That would take us 20 minutes that alone. Okay, so that's kind of miserable. Okay, so these are very long problems, because to solve this one very innocent looking equation with these initial conditions, we got a characteristic equation that it took 2 synthetic divisions to factor. Then we got the general solution. Then we had to do all this differentiating. Then we had to plug into this. And then if you were doing this completely, you would have to solve this system of linear equations. And that would take a while. So these are very, very long, complicated problems the way we're doing it. Okay, excuse me for that. Okay. Let's look at another example of another kind of a thing that can happen. But that one, we got 4 solutions. Those were all, we got 4, it was a 4th order equation, but we had 4 real distinct roots. And so we got exponentials for all of them. Okay, so that's a lot like what happened. It's an exact analog of what happened for the 2nd order equation. Okay, now let's look at another example. It's easier to look at this line by line. Okay, we're just going to do this and not worry about initial conditions on it. So we have a 4th order equation, a 4th derivative rather, plus twice the 2nd derivative, plus the function equals 0. Solve it. Find the general solution. So immediately we write down the characteristic equation. Lambda to the 4th plus 2 lambda squared plus 1 equals 0. This one, if you're clever, you don't have to use synthetic division on. You can think of it as a quadratic in lambda squared. In other words, think s is equal to lambda squared. Then this would be s squared plus 2s plus 1 equals 0, which you know factors to s plus 1 times s plus 1 equals 0. But s was lambda squared. So using that trick, you get it's lambda squared plus 1, quantity squared equals 0. Okay. So that means, how do you solve that? That means that lambda squared plus 1 has to be 0, but it's essentially a double root. And its lambda squared is plus 1 equals 0. So that says lambda squared is minus 1. So that says lambda is plus or minus the square root of minus 1 or plus or minus I. So plus or minus I is, each one of those is a double root because of this squared term. Okay. Now, when you had plus or minus I as an eigenvalue in the second order equations, what kind of solution did you get? Well, you thought of that as 0 plus or minus 1 times I. So when you write that down, you would get the solution would be e to the 0t times cosine t, and the other solution is e to the 0t times sine t. Okay, so we get the same thing here. We get an e to the 0t, which is just 1 times cosine t. And a second solution is e to the 0t times sine t. But it was a double root. So now we get t times that function, just like we did in the second order case when you had a double root, and t times sine. And now these are our 4 linearly independent solutions for our fourth order equation that we started with up here. So the general solution then is a linear combination of those 4 equations. Four functions. Okay. All right, so that one's not too bad.